The first speaker is Laurent Fargues of the CNRS, and he will speak about the Laumon Sheaf and the Langlands program for GL2 or higher degree extension of p.
Thank you, and thank you for the invitation. It's always a pleasure to come back here. Beginning with a formula to motivate everything. It's part of a joint work with Breuil. Here in this formula, E, the p-adic field, that is a finite degree extension of QP, or degree D. Rho is a mod P, reducible Q-bar coefficient representation of the Galois group of this p-adic field E. And in this formula, F rho is an étal local system attached to rho on something I will speak about later. SD of rho, F rho, is some symmetrization process, and this is what I will speak mainly today, this part, the symmetrization process. RH is some, oh, sorry, maybe I didn't mistake, some Riemann-Hilbert correspondence. J lower shrink is some extension by 0 as a solid quasi-coherent sheaf. Typically, I think the work of Lucas Mann. And F is a Fourier transform. Not a Fourier transform of like the Laumon Fourier transform, but of Mukai type. Fourier transform. Not the Fourier transform for D modules on an abelian variety, but the Fourier transform for coherent objects. Okay, that's different. Kernels. And here, at the end, it should be the p-adic local Langlands correspondence attached to rho, restricted to the mirabolic subgroup E star E1. Here we can conclude the Kirillov model of this local representation in those terms. This is an ongoing project, but for today, I speak about the symmetrization process only. Yes, I recall you the philosophy I developed at the MSRI in 2014. About the geometrization of the local Langlands correspondence. When the space is p-adic and the coefficients are l-adic, it's L different from P. We are able with Scholze, I mean, to develop this. Those ideas, I mean, in our recent work for l-adic coefficients and p-adic spaces, like Bungie, this stack of G bundle on the curve. For infinity, this is both primes are equal to infinity. This has been announced recently by Scholze using this liquid formalism. And today, this is what I spoke about a little bit. Today, I attack the PP case. The space is p-adic, the coefficients are p-adic, well, mod P, you have to begin with. Begin slowly. I mean, this is p-adic local Langlands. And I have some idea to switch the P to here, but I don't have time to speak over this. Thus, today, the keyword to remember, problem I'm looking at is holonomy. Of course, I mean, we're doing some, when the two primes are equal, I mean, we will look at d modules in some sense. I will speak about this. The sum warm-up. Recall the following construction that is due to Laumon, following the work of Schraen. Let's see of X, a smooth projective curve. Over a field, okay, let's say algebraically closed. And we have E over X. This is an irreducible QL bar local system on this curve. And for the datum is a curve, a local system, and an integer D. And we can look at the symmetrization morphism from X to the D, curve to the D power itself toward the symmetric quotient. We see it as the Euler scheme of the grid D effective divisors on the curve. That is sent D points X1, Xd to the divisor, that is the sum of the divisor defined by your points. What Laumon considers is the following construction, starting from this datum. Here, you look at the following, what I call the desymmetrization of E. As you push forward by this finite morphism, your local system E t times extensor product with itself. This has an action of the symmetric group, and you take the invariance. And this is a pervert sheaf on div D with QL bar coefficient. Okay, this pervert sheaf, you can describe it concretely, I mean, in this world, because this is, in fact, this is a construction that is very similar, I mean, from some point of view, with the Springer correspondence construction, but I'll speak about this today. This is, in fact, an irreducible pervert sheaf that is an intermediate extension of a local system FD that is quite complete. Yes, it's FD. It's the intermediate extension of FD. That's what is FD here. That's how you define it. You have UD inside the curve to the D power D times with itself. This is the open subset of points on the curve that are distant. And you can look at your symmetrization morphism restricted to this open subset. If we look at these multiplicity-free divisors on the curve, just here this open immersion, here. And here this is a Galois cover, the group, the symmetric group on D elements, and FD simply the local system associated with simply E conformity times with itself respective to this open subset UD with this Galois equivalent structure, sigma D equivalent structure, which defines by descent a local system like this. Okay. That's a very simple perverse sheaf, easy to describe. I mean, that's Laumon's construction. What I propose today, do something coherent. I dig everywhere in the literature, I mean, and I find nothing. Just today, instead of starting with an analytic local system, an état local system, E will be a vector bundle on the curve. X, the curve it will be. And define the following, same procedure as before. It's de-symmetrization. If you push forward E consorti times with itself by this finite locally free morphism p-adic, and you take variance under the symmetric group. And this is a coherent sheaf on UD. And the first remark, we have to work a little bit in general, is that, in fact, this coherent sheaf is a vector bundle. It's locally free. You have to check something in general when the characteristic is positive, but it's true. I found there's no reference for this type of thing in general. Okay, let's go further. I mean, into analyzing this vector bundle. You have a stratification by multiplicities. Of a divisor of your Hilbert scheme. Stratas, I will denote them. If D lambda underline X, well, lambda underline is what I call partition of this integer D. Let me be a little bit more precise, maybe. This lambda is a collection of integers that sum up to D.
By divisor of div dx, you mean a point of div dx?
Certification. Yeah, good point. Well. Oh, excellent. What I say, I mean, is not difficult. I mean, but the main point on all of this is to find a good point of view, the good definitions, not to go anywhere. Thus, more precisely, I mean, let's say lambda. This is a collection of integers lambda 1 to lambda r that sum up to D. And if I denote, I associate a symmetric group to such a partition of D. This is the stabilizer in the symmetry group on R elements of such a partition elements, lambda sigma of I. Okay. And Then you have the following description of this locally closed stratum div lambda underline. The following. So you have this open subset as before of elements in x to the r that are distinct 2 by 2. And there is an explicit UD lambda Galois cover with Galois group. This makes sigma lambda of this stratum. This map simply sends R elements on your curve point to the divisor sum of the lambda I, the divisor of the point xi. Thus, each stratum, I mean, has a natural Galois cover by an explicit group, symmetric group that is an open subset of product of the curve with itself. And you can verify the following. I did not, how do I name it? Lambda bar. The inclusion of the stratum defined by lambda as a locally closed subscheme of this D, then to pull back the current sense of your symmetrized vector bundle. This is the vector bundle associated to the sigma equivariance vector bundle on this Galois cover. Here you are a bundle that one. Where I have to be precise. T k of something. This is a degree k polynomial functor that is a twisted form of the polynomial functor that is taking tensor product k times something with itself on on the curve twisted locally on X. Thus, this means that we define and constructed this symmetrized vector bundle. It's a vector bundle, and there is a nice explicit formula for its restriction to its strata indexed by a partition of the integer D. This is given by some explicit, well, there's this non-explicit with it form I didn't speak about. Sigma lambda equivalent vector bundle on this Galois cover. But you can compute everything. And I have to say, here, I forgot, we have to suppose that D factorial is invertible in the base field. Okay, let's go further. Warm up. I mean, now I look at the compatibility with the Riemann inverse correspondence. I have two constructions. I mean, I have an entire construction that is due to Laumon. I took L, but you can take L equals P. I mean, it's work the same. I mean, I have a coherent construction. I mean, how does it work compatibly? I mean, what is the compatibility? Just here now, X, let's recall my also probably here at the institute. Everybody knows this. Suppose you have an FQ scheme where FQ is a finite field. Let's take out the following. You have a cat equivalence between FQ eta local systems X and coupled E5 where E is a vector bundle and phi is the semi-linear isomorphism between this is the vector bundle and it itself. This is to say an isomorphism between the Frobenius pullback of E and E. Okay, this sends F simply a local system, an état local system to F tensor O over FQ with a Frobenius identity tensor of Frobenius. This is classical local correspondence between local systems in characteristic P and vector bundle with a Frobenius. And this extends, work, this began history 20 years ago, with the work of Emerton and more recently, the work of Bat. And they extended this to correspondence, a Riemann inverse correspondence. Maybe I have to take some place here. For all étale sheaves, maybe not locally constant, RH, étale sheaves of FQ vector spaces on X, on your scheme X. This is an embedding inside the category of couples that may not be coherent. Here I took a coherent point of view. Let's say E5. I should change the notation. So now E is quasi-coherent only. And phi is a semi-linear automorphism. That this is my notation are not identical. Well, this is a Frog Q, Frog linear, linear isomorphism between E and itself.
What's the difference between a local system and a vector space?
This is of FQ, Finite sheaf of FQ vector space.
Is crop Q linear? Is that the same as over here, or is the Frobenius on the other side?
No, I have to change my notation because here this is, I should put the sorry. Let's put the big file here. It's a linearized version of big file. Maybe I didn't understand well your question.
The question is E living over the perfection of X or an X itself?
But that's the same, automatically it lives over the perfection of X.
Okay, so you're using the covariance.
Yeah. I mean, just with this notation, if I have F, let's say FQ local system, eta local system. With my notation, Riemann-Hilbert of F is the perfection of cats. Okay. The inductive limit, this cat correspondence of F and you perfect X. That you have to take a co-limit under forbearance. Okay.
Are there some finiteness assumptions implicitly? I mean, for instance, are the sheaves constructible?
Not at all. I mean, if you have a correspondence for constructible, you have a correspondence for any, because this is the one category of.
Okay, and how about X as a first
You
component?
can describe the essential image. But the point is that I will speak now. I mean, you can describe the image of constructible stuff as via some holonomy condition that are the perfection of coherent objects with the formulas. Right? I don't want to speak so much about this. Yeah. Blah, 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 blah. I don't know why. And thus, we have now the following proposition. Thus, I began my talk with a metal construction due to Laumon. I studied, a coherent construction, for fun, to warm up. And there is a both matchup via the Riemann-Hilbert correspondence. That is here. F. Now X is a curve. Back to my curve setting. Again, any scheme here, FQ scheme. Just F, this is an FQ eta local system on my curve. I can take it symmetrization. I like to I can apply the Riemann-Hilbert correspondence. And this is a perfection. Suppose that we take, let's say, E phi Riemann-Hilbert F, where E is a vector bundle. You have the symmetrization of the vector bundle. I explained. And you perfect that.
Wait, so the second Riemann-Hilbert is the cat version, not the perfect version.
I did a mistake. Oh yeah, sorry. This is cat. Well, I mean, this will be true to lose some content. Okay, which means the Riemann-Hilbert, the image via the Riemann-Hilbert correspondence of this symmetrized sheaf is a perfection of some explicit vector bundle. I call the holonomy property. It's globally that is linked, in some sense, to the perversity of this. It's not clear yet. Okay. There is a compatibility between the two symmetrization processes. Okay.
So what have you written at the top of RHF equals cats F what?
E phi is a vector bundle. Let's say phi is a semi-linear morphism from E to E. Imaged by the cat correspondence of this FQ eta local system.
And the top board, and the board above.
1 over A4. 1 over
This is this cat correspondence for this is U, some non-perfect object, a vector bundle. Riemann-Hilbert correspondence for this is a quasi-coherent object that lives over the perfection of the scheme in substance. And both match up via this co-limit under Frobenius process.
Description of SDFF as a middle extension, is that an L-adic thing?
It's an analytic thing.
Okay.
Up to now, that should be investigated. I don't know, because I mean, Gaber defined these structures, I guess, this Dwark thing, right? I didn't.
Definition is, for this, is that it's the push forward and then take a variance.
Yeah. This, if there is if it's perverse in any sense, it is perverse. I mean, it has to be. If the okay,
I think any
the factorial is invertible. I mean, in the base field, FQ, K, whatever. If not, you have to take the derived invariant order for it.
the perfection of any Cohen-Macaulay thing is perverse in Gaber sense. So it's going to be at least perverse. But
It has to be. I think it's a formality. I was lazy to reread Gaber's article. Up to now, I will speak about something now with the Lucasman context and so on. I mean, but I think this perversity property of this object in my context could be important at the end, which would allow you to add some new application of perversity. Okay. Okay, now the real thing. I wanted to do this, test a little bit. I mean, what's going on? I mean, there's nothing very difficult. If you're in bad Breuil, you can prove this easily. Thus, I take E, the finite degree extension of the p-adic number, degree D. And you look, obvious what's pi. Take the notation, my work with you also. The base point is diamond spectrum of FQ bar, the algebraic closure of the main field FQ. This is what we call an absolute Banach-Colmez space. This is a sheaf of global section of O of 1 on the curve. And this is isomorphic, non-canonically, to the spectrum, the diamond spectrum, if you want to know, of a formal scheme, FQ bar, one variable, and you perfectize. This is an explicit object.
I just missed what was Blackboard B? What is B?
What is B double bar? It's like a Fontaine's period ring, B plus Chris of something. But you can put some, it's a sheaf. I mean, B plus Chris, you can take B plus Chris of a perfectoid algebra, FP perfectoid algebra, and so on. Sorry, I mean, there is so much material in this business that I give some Allenberg lectures and there are some notes in my note de cours. I spent so much time on it. Go. Next talk, I want everybody to have the notes. I mean, I gave some lectures in Bonn too. I have some notes. Yeah, over 7 summer schools since the beginning of my career, 9 PhD students. There is, I don't know, maybe. Okay. Okay. You have this beast, this object. It's not a diamond. I mean, you have to be careful. But the fact is that I told you this p-adic local Langlands mod P correspondence that is very well known and very well studied. I mean, for E equals QP, thanks to the work of Breuil, Colmez, Kizin, Emerton, Pasquinas, plenty of people. I mean, everything is known. I mean, for E different of QP, almost nothing is known, everything breaks down. If you discuss with those people, it's a catastrophe, they tell you, I mean, say, okay, I'm going to try to do something. Let's say gamma E, this is the absolute Galois group, your p-adic field E. Over E. And the category of mod P, F2 bar, discrete Galois representation of p-adic group of gamma E, is the same as étal FQ bar étal local systems on what? On this list B Frobenius equals pi. Puncture it. This is a punctured absolute Banach-Colmez space, and we divide it by East. And this is what I call div1. In some of my articles, this is a moduli of degree 1 effective divisors on the curve. That is not the curve itself. If you heard about this topic. There will be a working group at the next semester on my job work, we shall see. Yeah. If you don't understand. Yeah. Because you will learn about this. And now, there is a Riemann-Hilbert correspondence between mod P Galois representation of like that and vector bundles on div1. This is an row. To some row define some kind of local system. And you extend the scalars to O, structural sheaf, and this is an equivalence of categories. You can give a meaning to this. You see Riemann-Hilbert correspondence, nothing difficult. I mean, and this is those objects here are Galois representation, and here this is what Fontaine called. I mean, this is the Lubin-Tate phi gamma modules. But I say, I mean, there's just a fancy way, I mean, in terms of language, to reformulate this Fontaine correspondence between Galois representation and phi gamma modules. This is just a Riemann-Hilbert, here it's a Katz correspondence this way. Okay? Just a language, I mean, nothing difficult. Okay. I won't use this one. I will rather use this object, punctured punctured Banach-Colmez space, and I will look on equivariant E star sheaves on this object for reason that this quotient is not perfectoid in general, but this one is perfect. Anyway, let's look first. Rho, the Galois representation. And I denote F rho. This is associated E star equivariant local system on phi equals pi minus 0. Okay, and rho is the same thing, but here it's a module on the same thing. Okay, the image, rho is the image by this Riemann-Hilbert correspondence between étal local system and vector bundles. Okay. I have to say this is not what the case of phi gamma modules considered by Fontaine, but this is the perfect case. Perfectization. That's very important. And now, there is a morphism, ID, which is my symmetrization morphism in this context. As in the beginning of my talk, we take the elements in this period ring, B Frobenius equals phi, that is non-zero, and you multiply them. Thus, take T1, D, collection of two I pi's à la Fontaine, multiply them, you obtain two I pi to the D. Phi times I, phi convenience of the product, phi to the D times the product. As a matter of fact, I have already studied this morphism some time ago. My another LNS article on the subject is that p-adic is quasi-polytal. This will be explained next semester at the working group, what it means. Surjective. And this is an isomorphism between divided by underline, and we explain what it means. That's a quotient. Well, there's another term because I don't take DFD, I take this punctured Banach-Colmez space and the targets. What is this delta D? Delta D, a collection of scalars. E star, the product is 1. That's an action of symmetry. Of course, if you rescale the T1 to the TD by some U1 UD, and you take the product, this is invariant, so this morphism is invariant under the action of this semi-direct product. But the point, this is a quasi-poetal isomorphism of poetal shape. I mean, what I mean is that the quotient is a poetal. It's a big quotient, it's a poetal quotient. Okay. And I mean, this result is the starting point of this work. This is quite a deep result with Content, I mean, long time ago, man. At any geometric point, the geometric characteristically perfect with field, any element of this can be written as a product of degree 1 elements. It's a difficult result, I mean, a quite deep result. Okay. And I forgot why I want to speak about this. And now, yes, we have our two objects attached to the Galois representation rho. We can define their symmetrization. That is to say, rho star F1. And the symmetrization of the coherent object, the associative domain, ou module. No module as an abstract object, as we speak about this later. Same form. Galois representation point of view, Figma module point of view. Okay, thus, I mean, that's stupid. This construction, I mean, define already a highly non-trivial functor, the greedy polynomial functor. From Q bar representation of gamma E. And I should say that from now, I will take the point from the state. D is a degree of E over QP. Which implies that the target of this morphism here is a perfectoid space. For this strictly less than the degree, it's not, it's a diamond. But here it's a perfectoid space. SD, this SD functor at the level of étal sheaves toward over convergence étal sheaves FQ bar vector spaces. On what? On this beast here. But it's perfectoid because, I mean, that's some fancy remark that is already in the work. On this quasi-compact Alice space, it's pas FQ bar, take the variables, x1, put the same algebra here, and you puncture it. If you can see. Sorry, it's difficult to read. Here, this is an explicit quasi-compact, quasi-separated adic space. The target is perfectoid, but étal sheaves are insensitive to perfection. Okay? Thus, you have those two categories that are elementary. I mean, Galois representation is simple. Category of over-convergent étal sheaves, I mean, on this explicit material adic space. Not complicated too, I mean. But this map, ID, between this Stein perfectoid space and this quasi-compact perfectoid space defines a highly non-trivial polynomial functor from Galois representations to over-convergent étal sheaves. And this is the object we want to study. And as in the curve case, the warm-up section has been too quickly. There is a nice stratification of your target, where you symmetrize this perfectoid space by partitions of the integer B. Okay. You can study it. I mean, I'm finishing to write an article. I mean, I study in detail this stratification. In general, strata are just locally spatial diamonds. They are not perfectoid. Also, the space is perfectoid. Maybe I missed something, but there's a nice stratification. As in the curve case, you can compute. The restriction of functor SD to this stratification. Explicitly. This mysterious symmetrization procedure when you restrict it, you pull it back to this stratification, it's explicit. Same result as I gave in the warm-up section. You can build something. Everything, this is the try to understand this construction. And I was led to the following conjecture. Maybe I should say something else.
Everywhere this phi that appears is all relative to E, right?
Yes.
Okay, I was having a little trouble with
This is a Q Frobenius. Pi is fixed, uniformizing element. Okay. At some point, I'm writing something. I mean, there's a section where I change the base field E for fun, but that's another story.
Okay, well, something just clicked with me now. As long as D is this degree,
Yes,
then,
that's a miracle.
oh, yes, I suppose.
That's a miracle. One of the main ideas, I mean, I was giving a talk in Beijing, I mean, and my Schraen was in the room, and we began to discuss a little bit about this. But the miracle is that for D equal this degree, this thing that is in general only a diamond is a perfect space. Right. And I'm going to tell you which perfect space it is. That's a miracle too. And this type of miracle, I mean, tells you that there is something deep. But maybe I should say something. Is that in fact, before going on, in fact, the symmetrization of the O module is the image by some Riemann-Hilbert correspondence of the symmetrization of the local system, eta local system. Here, this is à la man. This. There's a Riemann-Hilbert correspondence for overconvergent eta sheaves on anything, I mean, diamond of this type. Which implies, in particular, something non-evident from this construction, that this object is quasi-coherent as defined in Lucas manifest, which was not evident at all, I mean, from the construction. You have things to prove. This you have to, there's something to prove. Everywhere there's some proposition lemma. But now, come to this conjecture. That is a key point. Holonomic conjecture. That this symmetrized vector bundle hero has a module, well, quasi-coherent à la man module on this perfect weight space is completion, and this is where this is difficult compared to the algebraic case of Rock at the beginning of my talk. In the beginning of my talk, I said this is the perfection of something algebraic, which is easy to, but it's the completion of the perfection. Perfection with respect to a Frobenius of an O module equipped with a Frobenius with some Frobenius, let's call it phi, that is a perfect complex. Perfect complex as an O module. That is to say, this O module has locally finite free resolution by locally free O modules. Okay. But this is a coherence condition. This is to say, this O module is a completion of the perfection of a perfect complex with a Frobenius. What else? I check this E an equal characteristic local field. From the start in my talk, E was a p-adic field, but I mean, as you know, this theory has analogs, I mean, that are simpler. Everything is simple in equal characteristic case, in the context of Greenfeld modules and so on. Business. One of the theorems is the following. It is motivated by some discussion with Breuil. I mean, with that. That's why I introduced this holonomic conjecture. Because it implies that this symmetrized O module is generated by its global sections. And those global sections should be related to this p-adic local Langlands correspondence we want to construct for the absolute Galois group of E. Why? I should say this. I mean, for Jared, here it comes. Yes. There is an identification between the Iwasawa algebra, the canonical identification, the Iwasawa algebra of E as a locally propy group, and homomorphic function on this, let's say O plus 1 by 1. This is to say the global section of this seen as a module over the global section is a module over the Iwasawa algebra of E, and this identification is compatible with the action of E star. Here the E star is the one removed, I mean, somewhere. I mean, and here is a E star that comes, I mean, from the mirabolic. Thus, from any Galois representation mode P rho, you can construct a module over this Iwasawa algebra of E equipped with the E star action. I mean, and conjecturally, I mean, this should be pi of O algebraic dual. This is a construction that is used, I mean, this is not the smooth dual as a module over Iwasawa algebra. And yeah, that's why I mean this holonomic conjecture is motivated by trying to prove to construct explicitly some global sections. I mean, in those sheaves. Breuil, with a master computer in this domain, I mean, of p-adic Langlands, tried to do it by hand. Even using computers, it's even impossible. I mean, in some non-trivial cases, to prove that there is a non-zero vector. So, I mean, this holonomic conjecture, I think, is quite deep and non-evident because of the completion process. And I think I've been a little bit quick, sorry. Let's go to the working group next semester, and you understand if it is another lesson. Thank you.
Any questions?
Question. Earlier, I think it was raised already. You had this other, the RH, the Riemann-Hilbert from Galois representations, vector bundles on div 1.
Yeah.
What kind of space is div 1? Why do we have a Riemann here? Earlier, we had in the warm up, we had the Riemann-Hilbert for like curve over FQ, and then
Just scans, I mean, correspondence.
okay.
I mean, it's just that. E covariance equal to pi minus 0 is star E infinity flat, where E infinity over E is a completion of the limited extension. Related by the torsion function. Well, maybe Breuil. So infinity Breuil, and maximum orbital extension. Okay. And thus, I mean, étal sheaves on this. I mean, you apply cat correspondence. I mean, it's just a phi module. I mean, and there's a Galois descent datum, I mean, gamma. It's formal. It's okay. There's nothing difficult. Yes.
At some point, I think rho became a two-dimensional local system.
Yeah, I'm not here up to now, but I try to discuss, of course, with the experts, because this Colmez construction in general, for d equals 1, it's evident, this Laumon conjecture. I forgot to say this, because for d equals 1, you can replace the perfect phi gamma module by the non-perfect one, the original one used by Fontaine in his original article. If you look, by Kedlaya, classical. Why did I say this? Sorry.
Well, I just meant, I mean, in the title of your talk, it's about GL2.
Yeah.
And it sounds like you are allowed to put in whatever rho you like into.
Yes. I think this construction at the very end, I mean, gives complete nonsense. Maybe if rho is not two-dimensional. I mean, yeah. And I discussed a little bit with the experts, so I mean, rho has to be irreducible so that it is a good construction. Breuil, I mean, try to compute some explicit example for non-trivial extension of two characters. It's already extremely complicated. Yes.
Said, I think you said div 1 is the moduli of degree 1 effective divisors on the curve. Why is that not the same as the curve? You said it's not the same as the curve.
It's not the curve now. This is before the work we showed, sir. The curve S is an F Q bar perfect to its space. The curve attached to S, XS, family of curves is characteristic 0. Okay. But div 1 is characteristic P. That's div 1 of S. By definition, this is couples L, U. L is a line bundle on XS. U is section on L that is non-zero fiber-wise. That's the definition of it, degree 1. Okay, we'll see as a working group. I mean, it's too much material. I cannot say. I mean, Jared agrees.
Sorry, what?
That's too much to say. That's too much to say.
Okay, thanks again.